there's one situation that we don't have a good way of describing and analyzing using differential equations, forcing functions, and the Laplace transform, and that's sort of a momentary or instantaneous change to a system. So here's a good example of what I mean. If we have a 1 kilogram mass suspended from a 1 Newton per meter spring, and after a few seconds we hit this mass with a hammer, that's the sort of instantaneous change that I have in mind. So if we graph the force that the hammer exerts, since we're hitting the mass after 10 seconds, the force is, so this is force versus time, the force is 0 everywhere that's far away from 10 seconds, and then near 10 seconds, the force is very high, right? Just for a brief moment around 10 seconds. Now the question is how high, and what we're going to do ultimately is make this interval around 10 go to 0 so that this hammer blow is happening basically instantaneously, just in an instant. But before we can really write down a sensible formula for this function, we need to understand sort of how impulse shows up on this graph. So the unit impulse is really a change in momentum, and the units for momentum are force units times time units. So force units in kilogram meter and second units are kilogram meter per second squared, and time units are seconds, of course, and so the units for momentum are kilogram meter per second. You can see it's sort of like velocity, but it's velocity that's been multiplied by the mass of the object that's moving. So what we're going to do is come up with a way to write a function that describes an instantaneous impulse, an instantaneous unit impulse. And what we're going to do is have the impulse happening at time 0, and then we can shift it to any time we want. In particular, we can shift it to time 10. So I'm going to have an impulse that's happening. So this is going to be a graph of time versus force. And we're going to have an impulse that's happening at time 0. So this is like the hammer blow, but it's happening at time 0. And the force is going to be 0 far away from time 0, but near time 0, when the actual hammer blow is happening, the force is large. Okay, and so we're writing down an impulse, a unit impulse at t equals 0. Okay, well, you can see, so how is the impulse going to show up? Like, how do we know what a unit impulse is in this graph? Well, again, let's look at the units. So force comes in kilogram meter per second squared, and time comes in seconds. So our impulse here, kilogram meters per second squared, since it's force units times time units, impulse is going to show up on this graph as an area. So to have a unit impulse, that is 1 unit of impulse, we need an area under this graph of 1. So if you imagine if you think about how you can arrange for this area under the graph to be 1, how high this force is depends on how wide this interval is. The narrower this interval is, the taller the graph has to be to give you 1 unit of area. So since everything depends on how wide this interval is, let's give the width of this interval a name. And actually, I'm going to name the radius of this interval, so that is half the width of the interval. And I'm going to name this a. So on either side of 0, we're going out a units. So the width of this interval, where the force is non-zero, is 2a. We know that the area of this interval is supposed to be 1, or I'm sorry, the area under this graph is supposed to be 1, but the area is the width times the height. The width is 2a, and so that means the height had better be 1 over 2a. So this height right here is 1 over 2a. All right, so now we know how wide this interval is and how tall the graph is, now maybe we can write down a formula for this graph. One way to write a formula for this is you can see there's a step function that turns on at time negative a, right here, and then it turns off again at time a. So one nice way, so for sort of tradition reasons, we're going to call this graph delta. You might have expected to call it f for force, but we're going to call it delta. And since it depends on what a is, we're going to put a little subscript here, a, just to remind ourselves that this is the version of delta when the radius of this interval is a. So we're going to write delta sub a of t, and so it starts out 0, but then at time negative a, there's a step function that turns on. We know this step function has to have height 1 over 2a. And so to turn it on, right, we multiply by a step function. And this step function is turning on at negative a, so t minus negative a, so t plus a, minus, right, minus because we're turning something off. So we need to subtract 1 over 2a times u shifted over to time a. Okay, so this is a formula for this graph. Now, ultimately what we're going to do, or what we're going to want to do, is, right, the way we have this set up, our hammer blow is taking a length of time 2a, but a hammer blow is very, very quick, right? So any finite time is really sort of too long. Now, in reality, of course, a hammer blow does have a finite positive time on the order of, I don't know, microseconds, milliseconds, who knows? But what we're going to do is sort of mathematically idealize the hammer blow so that it happens in an instant. And an instant is when the width of this interval goes to 0. So ultimately what we're going to do is take this function delta sub a, and we're going to take a limit as a goes to 0. And we're going to call the resulting thing delta. Okay, so this delta is called the Dirac delta. And you might have noticed that I'm avoiding calling it a function, and that's because it's not really a function. If you look at this graph and take the limit as a goes to 0, this function will be 0 everywhere except at t equals 0. And at t equals 0, the height of this graph would be infinite, but that doesn't really make sense. I mean, it kind of makes sense, but what's the area under an infinitely tall spike? I mean, it's not well defined. So this thing delta, it's not really a function. In fact, it's something called a distribution, but what we're going to do is to work with it anytime we have some question about what delta actually does, how it works, we're going to replace delta with this limit and work with delta sub a instead, and then do whatever analysis we need to do, and then take a limit as a goes to 0. All right, so that's how we can describe this hammer blow. Of course, once we've done that in our original example where the hammer blow is happening at time 10, we can just shift this delta over to time 10 by replacing t with t minus 10. But before we actually do that, we're going to need to know the Laplace transform of delta, because delta is going to show up as a forcing term in a differential equation. So we're going to need to know its Laplace transform. So let's work out the Laplace transform of delta. And in particular, we're going to work out the Laplace transform of delta that's been shifted some amount, t sub 0. And we're going to assume that this is positive, right? Because the Laplace transform only notices things that happen starting at t equals 0 and in the future. The Laplace transform doesn't notice anything that happens in the past, so it really only makes sense to compute this Laplace transform when this delta has been shifted into the future instead of into the past. So let's actually compute the Laplace transform of delta. So if we use the definition of the Laplace transform, we'd run into a problem because the definition of the Laplace transform is an integral, and we know how to integrate functions, but delta isn't really a function. So that's a problem. So what we're going to need to do is resort to writing delta as the limit as a goes to 0 of delta sub a. So we're going to do that right off the bat. And we're going to move this limit outside the Laplace transform. Now, it's not obvious that it's okay to move this limit outside of the Laplace transform. That takes some justification. The Laplace transform is some sort of integral from 0 to infinity. So what we need to do is somehow justify why is it okay to move a limit outside of an integral. I'm not going to make that justification, but in this case, it is okay to move this limit outside of this integral, which amounts to moving the limit outside of the Laplace transform. So the limit as a goes to 0 of the Laplace transform of delta sub a of t minus t naught. Okay, so what is this? Well, remember, we wrote delta sub a as a difference of two step functions. And we know the Laplace transform of step functions, so that would be a nice way to calculate this Laplace transform. So it was 1 over 2a times u of t minus t naught plus a. Okay, got to be careful there to get the effect of a and this minus t naught all in the right place, minus 1 over 2a times u of t minus t naught minus a. Okay. So, fortunately, the Laplace transform is linear, so we can use that now. Limit as a goes to 0 of 1 over 2a times the Laplace transform of u of t minus t naught plus a minus 1 over 2a times the Laplace transform of u of t minus t naught minus a. Okay. And now we know the Laplace transform of a step function. So limit as a goes to 0 of 1 over 2a times, so the Laplace transform of this step function, so it's e to the minus the time shift here, so we have to write this as t minus something, right? Whatever is in these parentheses ends up as the coefficient here. And so we have to factor minus sign out here. It's t naught minus a. So we get t naught minus a times s. So that's the first Laplace transform. Minus 1 over 2a times, so we have to play the same game with this step function. So that what's inside this step function is t minus t naught plus a. So we get e to the minus t naught plus a times s. Okay, and we have to work out what the limit of this is as a goes to 0. So to work out this limit, why don't we first of all split up the exponentials, because the exponentials sort of have two pieces. There's a piece that depends on t naught, and there's a piece that depends on a. We really only need to analyze the piece that depends on a, because that's what we're taking the limit with respect to. So let's break this exponential up. Also, I'm going to factor out this 2a, so I only have to write it once. So we're going to get e to the minus t naught s times e to the as. Right, when we distribute this minus sign here, it turns into a plus on this one, minus e to the minus t naught s times e to the minus as. Okay, well, look, now both terms have an e to the t naught s, so we can factor that out and even move it outside the limit, because t naught, e to the t naught s, e to the minus t naught s, doesn't depend on a, so we can move it outside the limit. E to the minus t naught s times the limit, e to the minus t naught s as a goes to 0 of 1 over 2a. Let me write it like this. Let me write it as e to the as minus e to the minus as over 2a. All right, now to evaluate this limit, I guess what we should do is just try seeing what happens sort of naively when you plug in 0. When you plug in 0, you get 1 minus 1 over 0. You get 0 over 0. That's an indeterminate form that we can use L'Hopital's rule for. So let's use L'Hopital's rule. So e to the minus t naught s times the limit as a goes to 0. Now remember what L'Hopital's rule says is you take the derivative of the numerator with respect to your variable, and a is what's changing in this limit, so we take the derivative of this with respect to a, and what we get is the chain rule spits out a factor of s, so s e to the as minus plus s e to the minus as. And in the denominator, we get over 2. And I realize that now, all the way back where I wrote down the Laplace transforms, I missed a 1 over s, right, way back here. The Laplace transform of a step function times 1 should be this exponential divided by s. So this should have an over s, this should have an over s. There should be an s down in this denominator. And then we can factor that out and move it over here. And then over here. Okay. All right. So now that I've fixed this mistake with the missing factor of s in the denominator, we see that these s's all cancel. That's how I noticed I made the mistake. I knew this s was supposed to cancel, and it didn't. So let's try taking the limit as a goes to 0 again. Now in the numerator, we get 1 plus 1. The denominator is just 2, so that's 2. And so this limit turns into 1. So we get e to the minus t naught s, and that's it. So we've computed the Laplace transform of delta of t minus t naught. Notice that when we took this limit, the a goes away. And so that really justifies calling this exponential the Laplace transform of delta itself. It's because this limit turns out not depending on a, so right, delta is what you get when you take a limit with respect to a. So the fact that this limit is defined is what justifies calling this the Laplace transform of delta. So now that we have a Laplace transform of delta, let's actually use it.